Welcome. Thanks for coming to today's talk. Today we have Dr. Handley. He's a Royal Society University Research Fellow and Turing Fellow of the University of Cambridge, whose research centers around early universal cosmology and e-learning. His current research includes examining the consequences of early universal curvature and searching for evidence of cosmic microwave background at the beginning of time. He also works on novel machine learning Bayesian algorithms for high-dimensional parameter estimation and word comparison. Besides this, he studied the data analysis team for REACH and convened the Gambit cosmology group, who work on constraining extension of the standard model. So please join me in welcoming Dr. Handley.
Yes, thank you very much. So I think this is the first talk of the term, so I may have mispitched this in various ways. I've pitched it for undergraduate physics. So if you're in part 3 taking the relativistic astrophysics and cosmology course, you might find there are a few slides that I've stolen that you haven't seen yet in this lecture. If you are a practicing cosmologist, I can see at least one person here, you might want to just treat this as an audit for a public talk on cosmology rather than it being a technical talk. But hopefully there'll be enough technicality by the end that you have some idea about the kind of problems that modern cosmologists tend to think about. But much of this talk will be about trying to communicate to you what modern cosmology is and how it differs, certainly from the past, how it has differed over the past 10 years from much of the rest of the last century of cosmology. So in the first instance, before this works, is there a full screen button that's not working here? There we go, that'll do. Okay, so cosmology is a branch of astrophysics. And in particular, it studies the entire universe as a whole and considers its properties to answer questions like what is its age, what is its origin, what is its size, what's its fate, how big is it, and what shape is it, and what's in it. So whilst for since antiquity, these have been things that have been more philosophical questions, over the past 10 years, we now have precision answers to these questions. Namely, we know these to better than 1% answer. So the universe is 13.8 billion years old. It began in a hot Big Bang. It will likely end in an exponential expansion, although getting past data on our future is something you obviously can't do, but you might be able to infer things from previous eons if they existed. What's its shape? We believe that it's flat. Most of the cosmology community are flat universes. How big is it? It is infinite, but only just, but our observable patch is 42 megaparsecs. And what's in it? 70% of it is dark energy, 25% of it is dark matter, 5% is visible matter. And you kind of have these pictures of various versions of the universe that you can see. I'll have to gesture with this, I think. Here's the old heliocentric view of the universe that they would have had back in sort of medieval periods. And here is the more modern geocentric, but in an extended Copernican way that we think about the universe now that we'll come to by the end with this general picture that will also recur later in terms of the history of our universe. So before we get into placing the anatomy of our universe and indeed how we then observe that, I would like to encourage those undergrads in the room why you should consider doing cosmology as a research discipline. So it is excellent physics. You basically have to be able to combine both general relativity, quantum mechanics, particle physics, and thermodynamics all in one interacting, evolving mass in principle in order to get your head around it. And you are able to use the entire universe as your plaything to investigate fundamental physics. And more importantly, over your career, a suite of big LHC-like instruments are going to come online. We already have plenty, like Planck and like the James Webb Space Telescope, but the SKA, the Simons Observatory, the Extremely Large Telescope, the Large-Scale Synoptic Survey, or Rubin, Athena, Astrogram, these are all experiments that will be coming online over your research lifetime. Some of them in the next 5 years, some of them in the next 10 to 20 years. And in particular, the high redshift frontier that comes from doing gravitational wave observatories like LIGO, Virgo, CAGRA, LISA, and pulsar timing arrays, again, are extremely exciting. So not only do you have this very interesting theoretical discipline to think about, you have a wealth of observational data that you are able to play with to test out these theories and understand them. So it's real science, unlike what it used to be for the rest of the past century, where it was much more philosophizing about what we reckon might have happened in the early universe. Now we know what happened in the early universe, and we can start to use to do physics on it. And in particular, my area of expertise is the join between theory and observation, which is what's called inference, which is how do you actually push the frontiers of how you extract information from data in order to learn about scientific theories, in particular things like Bayesian inference, machine learning, and how, if at all, artificial intelligence can fit into science is the kind of questions that we like to think about. So We'll run through a few bits and pieces so you can get a feel for the scale of the universe and the various moving parts. For many physicists, hopefully these aren't completely new topics, but just to give you to kind of place you in our universe. Here's the Earth, you know where we are, and you will be able to name most countries and places and cities on that Earth. You probably also would be able to name most of the planets in our solar system. If you can remember the clean acronym of MAVENJA, you can then get through that. If you then move beyond our solar system, the next star is about 3 light years away. So whilst Earth is about 8 light minutes from the sun, and Pluto is about 45 light minutes from Earth, you find that the next star is 3 light years away. And this picture makes it look much busier than it actually is in our interstellar neighborhood. So you might recognize things like Alpha Centauri, and indeed, if you look around, you might recognize Vega as a possible star system, or Sirius. There's also Barnard's star, which you can see somewhere in this group. If you are an amateur astronomer, you may well know all these by heart or recognize these from bits of sci-fi from time to time. But these are our interstellar neighborhood, and there is not much in between us and the next star. These stars look very large, but they're tiny pinpricks in an almost inescapable void. You then blow up to our galaxy, which is made of about 100 billion stars. So whilst the nearest star from us is about 3 light years, the galaxy is about 100,000 light years across, 100 kiloparsecs, so about 300,000 light years across. And again, this makes it look much denser and much busier because most of this is empty space. You do get an interstellar medium that fills a galaxy, and people like examining the general properties and evolutions of galaxies, but galaxies are relatively sparse. And when galaxies collide, most of the stars will miss each other. That gives you a feeling of how sparse and how underdense they are. Whilst the gases will mix, the stars will very rarely be able to do it. They do pass through one another to a large extent. Moving up a scale, when you get to the local galactic group, it's slightly less sparse. So this is actually now to scale, in that here you will have a galaxy that you would measure in hundreds of kiloparsecs, and the next galaxy will be of order hundreds to megaparsec away. So this here, at a galactic scale, the universe looks a bit busier. In fact, so these are macroscopic objects on this picture, whereas in this picture, most of the Milky Way galaxy is full of empty space. Most of the intergalactic space is actually full of galaxies. So it's not as empty once you get up above galactic scale. You might recognize names like the Andromeda galaxy, and if you're an active astrophysicist, you'll recognize names like these NGC 185s or 147s as things that flash past you in various things, in various talks and seminars. Beyond the local group of clusters of galaxies, you then get to our supercluster of galaxies, and then above the supercluster you get to local superclusters, and finally the observable universe. So that gives you a feeling for the scale of our universe, where you have us as a star out of 100 billion stars in our galaxy, and our galaxy in our observable patch of the universe is one galaxy amongst about 100 billion. So it's quite a big place, but it is not so large that it's unintelligible. And in fact, many people say, doesn't astrophysics make you feel very small? And I would say if you're a proper physicist, you should actually feel quite big, because we're actually larger than the smallest thing we are by more than we are smaller than the largest thing that we are. So we're about 10 to the 30 beneath the size of the universe and about 10 to the 40 to 50 above the Planck scale. So we are actually bigger than average in log space slightly. So you should really feel vertigo rather than insignificance. Okay, so it's generally, this is a nice picture, and this is the kind of thing that you pick up in a textbook that you might have seen for a long time. But it's important to sort of stress that this is something that we see directly. And in particular, you get some interesting effects when you think about what the universe actually looks like to our naked eye. So that's our night sky. This is not quite what you'd see with the naked eye, because it's slightly enhanced by an infrared image of the Milky Way in the middle. But basically here you are looking from if our galaxy is shaped like a spiral armed galaxy, which we saw a few of those, we are about here, and the Milky Way is, if you are looking from us into the galaxy, this galactic bulge there is what we see in that left-hand image here. So this galactic bulge is us looking into the center of our galaxy, and that laser that's coming out of the VLT is a this is me getting used to this. That laser coming out of the VLT is a laser guide star. So this is a very clever bit of modern astronomy where you shine a laser into the atmosphere. You know the exact properties of the laser, so you can use a clever feedback mechanisms to deform the mirror at the bottom. It's called adaptive optics, and the mirror adapts to the fluctuating atmosphere to effectively subtract off the atmosphere in real time. And it's what allows you to get very, very high precision images of local objects from Earth, even though there's an atmosphere in the way. So that's our night sky, and this bulge of stars is the majority of our 100 billion stars in our Milky Way. If we look out beyond our galaxy, so we pick a patch of sky, we look between the stars and look with an advanced telescope, we can see a universe that is full of galaxies. So these now are not stars, these are all galaxies, and each point in this that you see is about 100 billion stars or so. You'll notice that this here, they form clusters where these things are similar colors, not because they're at similar epochs of the universe, and there's similar stars, galaxies in a given cluster. And you see the further away galaxies, these fine points are generally looking redder and things like that. This is an incredible image from the James Webb Space Telescope. I did enjoy myself updating all my 5 or 6-year-old outreach slides for the James Webb era, and it's pretty incredible. So if you then take this image, which is in a relatively local supercluster universe, and pick a new patch of sky that's semi-empty and zoom in on that with the Hubble Space Telescope, if you commission the Hubble for about 10 days, and you get it to look at that patch of sky for 10 days continuously as it orbits the Earth, kind of basically building up sort of photons as it collects more and more, you get this sort of slightly grainy image where these are some of the furthest away galaxies that you can possibly see. I'm now going to overlay the James Webb image of that same thing for 1 day of James Webb, which gives you this. So James Webb is a lot better than Hubble was, and it's many, many times better. In particular, one of the fun things to look at are, for example, these galaxies here, which there's nothing there in Hubble, but in James Webb, there's a big red galaxy, which is much, much further away, because James Webb sees further down the infrared band and can therefore see further and further away into the far redshifted universe. So this is a very exciting bit here. So there's a few points to bear in mind at this stage. These objects, particularly those red ones, are at high redshift. So you're talking things that are a good 13 billion years ago. And that ago comes from the fact that there is a time delay between the galaxies emitting those light and it reaching us today. So whilst the nearby galaxies give us an accurate picture of our current universe, the far distant galaxies give us an accurate picture of the universe when it was much, much younger. And remember, I made a statement earlier that the universe is of order 13 billion years old. That means you're actually looking at quite an early primordial universe when you look that far away with instruments that are that powerful. If we then go further and ask what is further than James Webb, and you turn James Webb onto a black bit of sky and you look further still, you find nothing. You get to the dark ages, because further than that, stars haven't formed yet. You're looking at a universe that is so young, the gas is still diffuse enough, it hasn't collapsed under gravity to form objects, and nothing is shining in the dark ages. So there are no stars in the dark ages. You've got this what's called cosmic twilight before, as the stars start turning on in cosmic dawn, and then reaching cosmic noon, which is when James Webb targets, and then the universe that we inhabit today is more like cosmic afternoon to early evening. We're kind of entering the slightly darker regions of the universe again today. So at that point, we get quite bored in principle, because there's nothing that you can see. And you might ask, why on earth would you look further than the dark ages, further than anything that might be shining? So there are no stars turning on, there's nothing emitting light at that point. So why would you look further? But if you basically crank down James Webb even further and look into the microwave spectrum, so James Webb can't do this, but microwave satellites can, you see something shining from behind the dark ages. So there's light that comes from before the first stars emitted light, and that light is the light from the beginning of the universe, or more precisely from when the universe was basically an entire star. Now that is the kind of thing that you can pick up in an old cathode ray tube TV, but we've gotten further than that in the past 10 to 20 years or so, where if you now look very carefully at that image, at those photons coming from the early universe, and try to subtract off the overall 3 Kelvin heat that comes from that, and look down to the millikelvin level that you might see, or the microkelvin level down further than that, you start seeing interesting patterns. So for example, the WMAP satellite can see these interesting fluctuating structures, which are sharpened by Planck and sharpened still further by ACT and the South Pole telescope. So this here is our image of the early universe. So in that instance, you see an overall heat coming from the whole universe when it was all hot and dense. But when you look in more detail, you can see also images, objects that are slightly in front. These are very early galaxy clusters that are causing something called the Sunyaev-Zeldovich effect to kind of pop these out of that there. So these are in the foreground, but that background cloudy-like structure are the fluctuations at the beginning of the universe, when the universe was about 300,000 years old or so. So now we can take a picture of that. So that's the first thing that I want to really get into your head. The cosmic microwave background is not just the afterglow of the Big Bang, it is our picture of the primordial universe. We can take a crystal clear snapshot of the universe when it was in a very early primordial phase. And this is the picture that you should hopefully have built up in your head as I scanned further and further away. Here's a picture of Hubble, because this image is from a while ago. Nowadays it would be James Webb, but you can see the late time galaxies, the ones that are close to us. And as you look further away, the galaxies get younger and younger. And eventually you get to a point where the galaxies are just forming. And then from behind them, you get to the dark ages, and then you get to the dark ages, and you get to the dark ages. And eventually you can see the bit that came before the dark ages emitting light from behind it. And one of the things that I do for a living is build experiments that try to image the dark ages by using the CMB as a backlight. So the idea, if you have the early universe shining through the dark ages, in principle, you can see stuff in between us and then that's not shining using what's called 21 centimeter cosmology. So called because the wavelength is that long when it's emitted. And if it's a redshift 10 or so, it's then about that long when it's received here, so about 2 meters in height, which means that if you stick an antenna that's about 2 meters tall in the Kourou radio reserve, you can, in principle, hear the first stars turning on in radio spectrum. Right. So here's a picture that I flashed up earlier. So this here is not true in any one direction. It's true in every direction. So if I look that way, I will see that happening. I will see the stars get younger, the galaxies get younger and younger and younger, eventually reaching a dark age and then reaching the early universe, the furthest light that we can see. That happens in all directions. So this here is a picture of Earth at the center, and it going out in log space to the planets, to the Oort cloud, to the spiral arm of our galaxy, to our galaxy, to nearby galaxies, to faraway galaxies, to the dark ages, and then to the cosmic microwave background. So this here is our picture of our universe with us at the center, but only in the sense that everywhere is the center, and you would see this wherever you were, okay? So this is the picture that you should have of observational cosmology, where you have time-delayed light arriving from across cosmic history onto our night sky, and what you see and can infer, because you have this epoch shell view of the universe as you look further and further away, you see a universe that is evolving. It starts hot, dense, and infinite in size. It cools and gets less dense and less dense as time goes on. And as it cools, the matter collapses into gravitational wells. It self-gravitates into forming things like galaxy halos that eventually form galaxies and stars and planets and people. So the idea here is you've got this hierarchical structure from something that begins hot and dense, expanding and then collapsing out of that Hubble flow. So some of this will be news to you, some of this won't be, depending on how you've thought about this in the past. But if you want to really understand this cosmogony, i.e. how our universe begun, you should try to make sure that you understand how to answer these questions. So when did the Big Bang happen? Where did the Big Bang happen? If the universe is expanding, what is it expanding into? What happened before the Big Bang, and why did the Big Bang happen? Understanding the correct answer to these questions is key to understanding the Big Bang theory and cosmology as a whole. So when is a relatively straightforward question. I've told you, and I will try to explain how we measure this later on in the talk, but I've told you it happened about 14 billion years ago. So the Big Bang happened a finite time in our past, quite recently, actually, because the Earth is also about 4 billion years old. So the Earth's a good third of the universe in terms of its age. Where did the Big Bang happen? Does anybody want to have a go at a one-word answer to where did the Big Bang happen? Everywhere is the correct answer. It did not happen at a point and expand outwards. The Big Bang happened everywhere, all at once, okay? So wherever you were in the universe, it was all hot and dense. The universe might have been infinite, it might have been finite, but wherever it was, wherever you were, it would be hot, dense, and is expanding. Does anybody want to have a go at the pithy answer to what is the universe expanding into? Because if you're a mathematician, you then start sort of mumbling about intrinsic and extrinsic geometries and maybe talking about balloons. But if you want the stop the smart ass one-word answer to how to what the universe is expanding into, what might you say? Itself is a good answer. The universe is expanding into itself, not into anything else, because it's space itself that is expanding. What happened before the Big Bang? It's not really a one-word answer to that, but there's a short sentence answer to it. So I heard there is no before, which is correct. There is no before the Big Bang. In our current theory, the Big Bang is the beginning of time. It's a singularity at the center of our equations. That doesn't mean that one day we might not have a better theory or a better bit of data that allows us to answer those questions. But for now, there is no before the Big Bang. And as to why, observations do not tell us that. So we do not have an answer to why the universe is here. All we are at the moment as cosmologists is cosmic historians that can track back from today and see back to a universe 300,000 years old. We can directly simulate in the Large Hadron Collider back to a few microseconds after the Big Bang. And there's a small other subtlety that the nature of the expansion of the universe at early times means that it acts as a microscope onto an even earlier epoch. So we can, in principle, with certain theoretical assumptions, probe the universe when it was 10 to the minus 32 seconds old, using the CMB as a magnifying glass onto that period. But that does need you to assume quite a lot in order for you to make that inference. But the clear thing here that I want you to understand is we see the Big Bang in the sense of the hot, dense, early universe phase. We see that directly and we image it and take pictures of it. So this is not some abstract theory. This is a precision science. So if you want to be a precision scientist and you want to model the universe, in general, when you're putting together an idea about what the universe is, you need to describe what's in it, how big it is and what shape it is, and how it started and how it evolved. So this content, size and shape, initial conditions and evolution. And over the past 10 years or so, for the past 10 years or so, and over the past 20 years, we have assembled what's called the standard model of cosmology, which is easily confused with the standard model of particle physics. So we talk about now the ΛCDM concordance model. It's always a bit embarrassing to spell out ΛCDM because it stands for the two big fudge factors we have to put into the universe to make it work, namely cosmological constant lambda and cold dark matter, as in the two dark elements of this. We'll come on to this later. But fundamentally, we say the universe in content is full of dark matter and radiation and some dark energy that's necessary. It is flat, homogeneous, and isotropic to within experimental error, which means that when we look at the faraway universe, although we see a time delay and a younger version of that, we see no significant evidence for us being any different in particular from any other bit of the universe statistically on average, and that being true in all directions. And we also assume that its evolution is dictated by Einstein's theory of general relativity. So the thing that drives the gravitation and the expansion of the universe and everything else is basically fundamentally Einstein's general relativity. That's our concordance model, and that's the baseline. If you're a cosmologist, you try to break that or to make it better or to disprove bits and pieces of it. ΛCDM introduces 6 unknown quantities a priori, 3 for its constituents, 1 for its scale and shape, and 2 for its initial conditions. Constituent-wise, the first is the amount of normal matter that being cosmologists or astrophysicists, we call baryons in a way that makes particle physicists shiver. Baryon just means not dark matter. So basically all of the leptons and photons and all that stuff there, we just call them baryons in the same way that we call anything higher than helium metal in cosmology, and again makes people feel funny. We also have the fraction of cold dark matter in the universe. You may have heard of dark matter. Cold dark matter is different from hot dark matter in that it is at low temperature, so it's not relativistic, and it sort of clumps and forms halos and things like that. And we also have to assume something about the cloudiness or the optical depth to the CMB, this tau parameter. This is not essential that you follow all of this, but it kind of gives you a feeling for the overall, not fudge factors, but free parameters that in principle we don't pin down. We also need to assume something about its scale and shape, which we assume to be flat, and to have a present day expansion rate of h0. We will come on to this later. So h0 will loom large through this talk. And in addition, something that I definitely don't have time to go into, you have the initial conditions which are parameterized by a near scale invariant power spectrum of primordial fluctuations in curvature. From these flow a host of derived quantities. So from those 6 things we don't know, you can make immediate statements about the dark energy, the radiation content, the neutrinos, and various other things like its size, its shape, and all these other things here. But it's important that any of these can be adjusted, extended, removed, and tested and said, does the data prefer this model to this one here that the community has settled on by testing it against data? So you could ask, what if I make the neutrino sector slightly more interesting? What if I add an evolving dark energy? What if I make the universe curved? What if I remove Einstein's theory of gravity and replace it with some modified theory of gravity? All of these things are in principle testable against the data that we see today. As an example, we'll start with H0. So a university challenge question, in what units is the Hubble constant measured? Anybody know to hand? Be buzzed away by now.
Meters per meter.
Meters per meter. It's a flippant but funny answer. Cosmologists have a habit of picking stupid units like millimeters of mercury per volumetric megaton. I think that, yeah, that is the units of the Hubble constant. It's in kilometers per second per megaparsec is the measurement of the Hubble constant. This sounds silly, but it's not, because it's basically recession speed over distance. So if the Hubble constant is 100, that means when you are 1 megaparsec away, an object 1 megaparsec away from you appears to be moving from you at 100 kilometers per second. If you were 10 megaparsecs away, you would be 1,000 kilometers per second. And if you were 100 kiloparsecs, it would be 10 kilometers per second megaparsec, if Hubble were 100. So these are all sort of, it's something that seems a bit weird, but Hubble, those units are things that are typical galaxy speeds and typical galaxy distances. So that's why you measure it in something that is kilometers per second per megaparsec, and try not to think too hard about the fact that in SI units, that's just got units of 1 over time. So why do we have 2 distances in there? In order to measure the Hubble constant, if you want to do it the obvious way, you would want to go away and measure distant galaxies and ask, how far is it moving from me? And how far away is it? How fast is it moving away from me is actually quite easy. We can do that with redshift. You need to be careful because you want to disentangle the overall global redshift that comes from the Hubble flow and a peculiar velocity redshift that comes from it happening to move towards us, or being, say, dragged towards a nearby object that's decoupled from the Hubble flow. But redshift is the one that we're quite sure about. So if you can tune a spectrometer on a galaxy, you're usually happy to say, I know how fast this object's moving away from me. But how far away it is much, much harder. So as a demonstration, as much as a cosmologist can, how do you know how far away this pen is from you? If it's close enough to you, you can use stereopsis, i.e. the fact that you have 2 eyes to kind of measure actually the distance and the fact that there's a mismatch between those 2. But further away, like this pen is from you, you don't really have any, you don't get any gain from having 2 eyes from looking at this pen. And if you want to ask how you know that the pen is closer to you than I am to the screen, for example, or that the pen is between me and the screen, what your brain actually does is it moves your head very slightly and tests the parallax. So as you move your head from side to side, you see the pen moving very slightly, and your brain is very good and your eyes are very good at picking up that very subtle difference. So parallax is your gold standard measurement for how far away things are. We've even heard the word parallax already in this talk when I talked about parsecs. So if you've heard of Star Trek using words like parsec, it's an actual astronomical term. Does anyone know what it stands for? Parsec? No. So it stands.
Parallax is 1 arc second.
Yes, so it stands for parallax arc second is what parsec is, and you're correct that the parallax is 1 arc second. So obviously, if I look at the night sky and move my head from side to side, that star does not move relative to the other stars in any meaningful way that I would be able to pick up. However, if I wait half a year, the Earth moves quite a long way around the sun, and then those do move a little bit. However, the amount they move is by, if it's 1 parsec away, which is about the distance to the nearest star, the amount that the nearest star moves is 1 arc second. You've heard of hours, minutes, and seconds. you have degrees, minutes, and seconds. So an arc second is a 60th of a 60th of a degree on the sky. So when you look at our nearest star, it moves by a 60th of a 60th of a degree, and we can pick that up with telescopes. In fact, we can pick that up almost all the way to the Milky Way, to the center of the Milky Way now with the Gaia Space Telescope. We are very, very good at measuring parallaxes. So we can get a very clever, clean measurement on most of the stars in our galaxy. But that's no good if you want to know how far away another galaxy is, because you can't measure the parallax of the galaxy relative to the Earth's motion. And we don't move fast enough around our galaxy because that takes 200 million years, and we're probably not going to be doing anything particularly strong there. So to do that, you need to use other techniques. And the three methods that you use to move from parallax of stuff that's nearby to further away things are standard candles, standard rulers, and standard sirens. Okay. Standard candles are, in principle, an easy idea. If you knew exactly how bright something was, and you had an object that was nearby and was that brightness, you could then compare that bright object to an exactly the same bright object that's further away and ask, how much dimmer is it? And use that to work out how far away that object is. Now, if you're doing the relativistic astrophysics and cosmology course, you will learn there are some subtleties that come with the expansion of the universe that change this very slightly, in particular as the universe changes in volume. But fundamentally, it's the same idea that dimmer objects are further away. And therefore, if you knew exactly how bright something was, you would be able to determine relative distances. So if you had an anchor that was in that parallax sector, you would be able to measure how far away everything else is in the universe. Now, of course, standard candles are not easy to come by. You can't go lay out standard brightness objects, so you need to rely on a physical mechanism that creates objects of a standardized brightness, or at least a standardizable brightness. And one of the best tools we have at the moment is our type 1a supernovae, which are these pairs of stars where you have a white dwarf and a normal sort of main sequence star or red supergiant. And because it's overfilled its Roche lobe, which you probably won't have, you might have covered in part 1b, perhaps. At that point, the larger star starts pouring matter onto the other star. And as it pours matter onto that other star gets bigger and bigger and bigger until eventually it reaches certain critical limits like the Chandrasekhar limit or otherwise, and then detonates. And because that process is quite steady and careful, it means that that's got a very clean profile, so that when you plot in a normalized way these light curves on top of one another, you have a standardizable object. So that physical process creates something that is roughly constant brightness. There's a lot of subtlety in that statement that I'm not going to go into more detail than that, but it allows you to build up this image here of objects where you have redshift on the x-axis and how bright it is on the y-axis. And you can see here, or how dim it is on the y-axis. So they get dimmer as you get further away, basically. And this here shows, again, that brightness against time. So supernova blows up and it gets dimmer. And because the way that it blows up and gets dimmer is very similar between different supernovae, you can use that to create a standard candle. That's, in principle, the easy way to do this. The trouble is that in practice, these are very difficult to standardize properly, and they are beset by many things that can go wrong, including many of the personalities that work in this field. So it's very hard to argue against some of the Nobel Prize winners in this field, because they are, I mean, they've got a Nobel Prize, but also they're very militant about how you do this. The other way to do it is standard rulers, okay? If you knew how big something was, in the same way that if you knew how bright something was, if you knew definitely how big it was, you could determine how far away it is. Now, obviously, it's very hard to imagine how you could know how big a galaxy is, because a galaxy's size is driven by the amount of stuff in it, and there's no real kind of way that you would know exactly how large it is. But physical processes do often have length scales associated with them. So if you imagine some radio jets, so some kind of very high energy active nucleus pummeling matter into the intergalactic medium, eventually it peters out when it reaches a certain critical density. That process is quite well defined. So if you knew other things about that, you might be able to estimate how big that ruler is. Nobody's managed to do this yet, really, but in principle, that's the kind of clean idea. How people do it in practice is by looking for correlations between galaxies that come from ripples from the beginning of the universe. But the main one I want to focus on here is the cosmic microwave background. So here you can see a whole sky picture of that fuzzy gray image we saw earlier, but taken by the Planck satellite and colorized. This here is not white noise. It does not look like the stuff that you might come out of a cathode ray tube. It has a certain structure to it, so that such that when you look at the Fourier transform, there are certain peaks and troughs in this, and these are standard length scales. So this main big peak one is the one that the eye picks up quite well. There's a clumpiness of redness and a clumpiness of blueness that you can see that looks like a certain rough size, and it's about that big. And that does give you, in some sense, a standard ruler at that very early epoch. There are subtleties associated with the statement, but fundamentally, the ripples here have a characteristic size that, given the right degeneracy, you can break and find how big these objects actually are, and therefore measure how far away things are. The other thing you can do is standard sirens. So these are super new, and we're now talking about things that are within the past 5 years or so. So we detected gravitational waves for the first time in 2015. This was a very exciting event because A, it proves Einstein's theories, one of Einstein's predictions from about 100 years ago, correct. But more importantly, it was our first example of using something other than light to look at the universe. Because gravitational waves are not just detections of ripples in space-time. They are, in the same way that a telescope detects ripples in the electromagnetic field, a gravitational wave detector detects ripples in space-time, and that is a messenger that you can use to infer things about objects at distance. So you can use gravitational waves as a telescope, okay? And in particular, in 2017, we had this truly incredible result where LIGO, which is the two gravitational wave detectors, heard a gravitational wave starting to get to its merger phase at a long time. And I say the word heard because if you can see down here, this axis here is frequency, and it goes from 50 to 400, which is around sort of middle C or so. So these are things that in principle, if you play them out loud, you can hear them as notes because they are. This is a very deep note that's too low for my baritone. But over time, over these 10 seconds, it goes like that. And it's called a chirp. And LIGO heard that rumbling note from about from a few sort of seconds before and said, everybody go and look over there because there's about to be something interesting that happens exactly at this bit of the sky, and that LIGO and Virgo said it was here. CAGRA did not find something, and therefore gives you further localization. And then we turned about 40 different telescopes onto that bit of sky, looked at that, and saw a gamma ray burst go off. It has long been thought that gamma ray bursts were the merging of black holes and or neutron stars, and this proved that this was the case. What we watched is two neutron stars colliding together. So if you take a star, compress it into something about 3 kilometers in radius, take another star, compress it to about 3 kilometers in radius, and then smash them together at about a third the speed of light, you get this very energetic event, or this very energetic event that is sufficiently energetic to create gold. So supernovae are not energetic enough to create gold, but merging neutron stars are. So if you are wearing any gold jewelry, you're wearing bits of merged neutrons star from a few billion years ago. And this was us watching that. So we saw a gamma ray burst go off, and then after a few hours, we saw gold appearing in the spectrum that was not there before as it moves into the intergalactic medium. About a third of an Earth's worth of gold was created in that event that we watched. So this was very cool because it is an example of a standard siren in that you have a measurement of how far away something is very precisely from the gravitation wave event and how bright it is from the gamma ray burst. And those two together give you a measurement of Hubble that is very good in that one event. It's about sort of 10% accurate, which is madness for a single event. We were therefore really excited and thinking, let's just wait for a few more and then we'll have this new perfect way of measuring the early universe. None have yet been detected. And it's looking increasingly like this was an unusually rare event. And we are hoping that future versions of LIGO might pick up these events. But for now, we are seeking other alternative strategies to these what are called bright sirens, including things like spectral sirens and dark sirens. But I can talk about that if there's time at the end. So here is the Hubble tension that the title refers to. If you use the CMB and you ask what is the current expansion rate of the universe, you get 67.4 plus and minus 0.4 kilometers per second per megaparsec. If you use supernovae, you get 73 plus and minus 1. And I don't know how good your math is at this point, but those two numbers are not the same, and they should be. So if you plot those on a curve, you find that this here is what the CMB tells you, and this one here is what the supernova tells you. So here I'm plotting H0 on the x-axis, and here I'm plotting the probability density of H0 on the y-axis. So you can see here it's centered on 67.4 plus and minus 0.4, and here it's centered on 73 plus and minus 1. It feels like I'm belaboring a point for no reason, but there is method to my madness. We call this discrepancy between data sets a tension. And here we have a fun plot that shows year 2000, 2005, 2010, 2015, 2020, showing measurements of the Hubble constant across human time. So in the early 2000s, you had early supernovae surveys and early CMB WMAP surveys giving you consistent measurements of the Hubble constant that was originally about 72 plus or minus 10, 72 plus or minus 5, and so on and so forth. But as time went on, we watched the CMB values refine around this lower value, and the supernovae values refine around this value. You can also see here plotted the standard siren measurement, this one here, which is my big 10% measurement of this Hubble constant that's very impressive, but still consistent with both. And ideally, we would want to get a few more to hopefully split the difference and work out which of these two is correct. So 5.6 kilometers per second per megaparsec might not seem like a big difference, but this is a 5 sigma in certain sense of the word discrepancy. This is a problem because it means something is wrong with our model of the universe. These two should be the same, and the fact they're not means that if both teams have got their measurements correct, then this means we need to change our model of the universe. And the last time we did this, we had to come up with a new idea like dark energy. But nobody has yet found a convincing solution. And this was about, if you actually go really to it, it was Planck 2013 was when we first started seeing this big discrepancy, and Shoes being the Adam Rees latest version of this, being the one that really sort of made people start to worry once we've gone beyond the Carnegie project. And now here we have, and now here we're in the stage where these are definitely different in a way that we're not very happy about. And here, this would be how good the experiment would be if we had 15 of those standard sirens. This is how good it would be if we had Planck and S4 measurements. And this is how good we can expect supernovae to be in the next 70 years, given how many supernovae we think we're going to measure, because we know roughly how often they occur. This is not the only tension, though. There are other things that can go wrong with our models of the universe. This is a famous plot. On the y-axis, we have amount of dark energy in the universe. On the x-axis, we have amount of matter in the universe, or rather fraction of matter. So here you have a universe that's entirely matter and no dark energy, and you have a universe that's entirely dark energy and no matter. And here you have universes that are more than 100% matter and dark energy. So try not to think too hard about what more than 100% means in this context. But interestingly, you find that you get different kinds of universe. So for example, universes around here are the usual kind that begin in a Big Bang and keep on expanding forever. Universes below this line eventually recollapse in a big crunch. Universes over here don't have a Big Bang. They've got a bounce at the start because the dark energy is strong enough to cause a bounce. And universes along this line have a geometry that is flat. Universes above are closed and here are open. The natural question a cosmologist asks back in the 90s or 2000s for Spergel and for supernovae and CMB and clusters is, which is our universe? And no one of these measurements, supernovae, CMB, or clusters, gives us a definite answer. So if we focus on this 2003 supernovae measurement, so we've obviously updated this, supernovae tell us our universe is somewhere in this region here. This here is a two-dimensional probability distribution. In the same way that this earlier one was a one-dimensional probability distribution, this here is a two-dimensional distribution of the two cosmological parameters omega lambda and omega m. And supernovae tell us it's somewhere in here, clusters tell us it's somewhere in here, and CMB tells us somewhere on this line here. And in that sense, you can see that it's nice that these are coincident. And in fact, it's in combination that we're able to pin down the properties of our universe. And this idea of merging complicated data sets is something that people have been doing in cosmology for some time now. This is what this plot looks like nowadays. So first of all, note this went from 0 to 3 and -1 to 3 here. Now we're going from 0.2 to 0.6 and 0.5 to 0.8. So this is zoomed right in a small box. And you can see here, supernovae, baryon acoustic oscillations, and CMB now look quite different from one another when you plot it on this plot, in particular, if you let curvature float. You find that these things do not overlap with one another in the way that you might imagine they should. Okay, this is therefore interesting and is another version of this problem with, as we've got better and better data, we've found cracks in our models where these things no longer line up. And if they no longer line up, there's something missing from our model, and that's quite exciting in principle. I've also been kidding you a little bit. It's more complicated than that. This here is, I mentioned there were 6 parameters in our universe. This here is the 15 pairwise projections of that 6-dimensional probability distribution into the plane. So you've got some 60 distribution of those parameters. And here we're looking pairwise in each of these here. And down the diagram, we're looking at the single parameter projections. You obviously can't plot a 60 distribution on a bit of paper. So what you should really do is manipulate the underlying Bayesian inference machinery beneath that. That is what cosmologists have been doing for some time. This sophisticated Monte Carlo machinery for understanding measurements of parameters that go beyond a simple error bar. So just to kind of highlight a few things here, you can see down here, this is omega B. This is the amount of normal matter, baryonic matter in the universe. And you can see here, this distribution is centered on about 0.05. So that's where our 5% matter comes from. Here you can see omega C, cold dark matter, is centered around 25%. If we had another one for dark energy, it would be centered around 70% in this plot. Note, however, that you don't make a simple clean measurement of H0 and omega B. You get this interesting shape that means that in universes that are expanding faster, you predict a lower value of the omega B, and a universe expanding slower, you'd predict a higher value of the amount of matter in the universe. And this here is basically a souped up error bar. So i.e. it's error bars, but expressed as high dimensional probability distributions in multi-parameter spaces. And that's this sophisticated Bayesian stuff that cosmologists like to think about and to examine, and to ask, what's the next measurement that might break this degeneracy to allow us to learn something better? There are certain tensions that only show up in this full picture, in particular things like the weak lensing tension. I have of order 3 minutes left. This is something which, if people are interested in, I can talk a bit more about. But one of the things that I spend my time thinking about a lot is the tensions in how we do data analysis. So in Rumsfeldian terms, known knowns are the current theory, and unknown knowns are new theories. This might be things that we know that, that might change. Known unknowns are the way that we currently analyze the data and the errors and things like that. And the big thing that keeps cosmologists up at night are the unknown unknowns, which are systematic errors that are not accounted for. And this is the thing that most of us, if we were asked to put money in it about the Hubble tension, would say, it's nice to imagine that there's such a big discrepancy between the Hubble parameters measured by supernovae and the CMB, but in reality, supernovae are very hard objects to manipulate, and it's more likely that there's something a bit wrong in that analysis than there's something so broken in the theory that it's at the 5 sigma level. We're happy to be proved wrong, but because most scientists are usually quite skeptical and conservative with a small c at heart, they tend to assume that it's generally probably somebody's messed up than the theory is completely wrong. We will see as time goes on, as more data is laid down to this. But one of the things that I like to spend my time on is pushing the frontier of data analysis using simulation-based inference, which is a way of being able to put in systematic error accounting much more easily and much more effortlessly than you do in current setups. And it's also important, just to mention at the end, there are theoretical tensions. The first one is the initial conditions of the universe that are to a large extent explained by the models of inflation. Some people don't like inflation because it doesn't really feel like science. And some people argue that even if it is science, it just moves the problem of initial conditions of the universe backwards in time. There's tension in entropy in terms of why did the universe emerge in such a low entropy state, or equivalently, why is the thermodynamic and expansionary arrow of time aligned? The elephant in the room, however, is the dark tension, i.e., why do we need to put in 70% dark energy to make anything add up? And most cosmologists would be perfectly happy to take out dark energy and replace it with something more satisfactory if they were convinced. You would struggle to get us to convince us to get rid of dark matter, because dark matter is a much more, if you like, in principle, well motivated and much more supported by a variety of data sets than dark energy, which is really just something we've observed in the past 10 years or so. And then again, you've also got the problem that we don't have a predictive theory of quantum gravity. And one of the excitements that people like to think about is that what if in 50 years' time, people will look at this time and see these measurements in cosmology where cracks are forming in our theory of gravitation and the contents of the universe, if this is where we need a new version of physics in order to come up with this. But it may be that we've just got the measurements wrong. So, more measurements. We've got the European Extremely Large Telescope coming online. This is a successor to the European Very Large Telescope, which was then, no, it was the Large Telescope from Europe, the Very Large Telescope from NASA, and the Extremely Large Telescope from Europe again. NASA reportedly had plans for an OLT or a ULT, which stands for the Overwhelmingly Large Telescope, or the Unreasonably Large Telescope. Here you can see an artist's impression of what it will look like, and here's it where we've taken the top of a mountain off in Chile and are now building this 40-meter telescope, which is madness. It's just so big. It doesn't sound big, but it's much bigger than everything else. In principle, over its baseline, the ELT will be able to watch the universe get bigger, which is an interesting sort of statement in itself, but we'll do a lot of other science along the way. The square kilometer array is a big beast of radio astronomy, the kind of things that you see down at Lord's Bridge, that but multiplied by a lot. Square kilometer, it's really 13 square kilometers in size, and that's collecting area. So the number of dishes it's got on the sky is 13 square kilometers in size, which is big. That's the kind of machine that keeps scientists up at night because of the data rate this will generate. You have to forecast how powerful computers are going to be when it's turned on in 10 years' time, which is a lot more powerful than now, and work out will we be able to process that data? And the answer right now is no. So we're trying to build better algorithms for being able to process data at that rate, including things like machine learning. You've obviously got the James Webb Space Telescope. This gives you a feeling of its size. This is not the actual thing. They did not let it out of the clean room for a photo op. But now that's working astonishingly well and giving us some very interesting bits of understanding of galaxy evolution and possibly even some cosmology. And the main thing that I would really stress for your generation, it's gravitational waves. This is our new window onto the universe and will be the gift that keeps on giving as we move into the high redshift frontier and are detecting more and more objects than we've ever seen before, which we know will happen. It's a very inevitable thing. If you're thinking about PhDs, gravitational waves can't go wrong. So I would recommend that. And again, just to kind of flash this up before the end, cosmology is great fun. There's loads of problems and loads of data, and that makes it unusual as a proper blue sky science, in particular, if I'm going to be mean, in contrast to particle physics, where they built the big machine and they found the Higgs boson and there's nothing else. Whereas here, we've got lots. So if you're a scientist that's agnostic about field, cosmology is a much brighter future, in my view. Many thanks.
Thanks so much for the wonderful talk. We actually have time for a few questions, so please ask that.
Good. Just shout.
Yeah.
I can repeat.
Could you tell us more about what the background you get to see the dark ages?
So how could I tell you some more about how to use the cosmic microwave background to see the dark ages? It's a good question. So if you go over right.cam. So you understand the principle that there is this period from which the CMB shines from behind, and you're using it effectively as a backlight. Yes. So there is a specific transition in hydrogen called the hyperfine line that you can't see in a lab because it's too difficult. It's too small a measurement for you to actually detect at lab level, but you can see it in the universe because there's a lot of hydrogen in the universe. Clouds of neutral hydrogen, when being shone by the cosmic microwave background, which today is a 3 Kelvin temperature, and back in the dark ages would have been about 30 Kelvin, because the universe is about 10 times more dense at that point, or 10 times more smaller in a scale factor, 1,000 times more dense. A 30 Kelvin thing shining through a cloud of hydrogen will be absorbed by this hyperfine splitting that basically comes from the fact that the proton in up or down phase, depending on the electron, has a slightly different energy. So if you've got a hydrogen atom, proton and electron, if they're spin aligned, that's one energy. If they're spin anti-aligned, that's another energy. It's a tiny difference, but you can see it on cosmic scales when you have a universe worth of hydrogen, and it actually lights up very clearly. So the principle is you're mapping hydrogen in the universe using the 21 centimeter line of neutral hydrogen, is the short answer.
Can I ask what specific machine learning techniques are used for simulation and data analysis?
So it's obviously a bit, so the question was what specific machine learning techniques are used for simulation and data and things like that. It's a bit of a wild west. And scientists are generally very skeptical of machine learning because they don't want, particularly if you ask ChatGPT what the value of the Hubble constant was, that's not science, right? If you use machine learning to speed up a bit of a simulation that you understand very well, that is science. You're just basically, it's a fancy interpolating function that speeds things up. And it's the bit in between that we're a bit concerned about. And in particular, the thing that I alluded to very briefly in terms of this simulation-based inference, this, in my view, is the way that we'll be doing data analysis all the time in 20 years. So in the same way that nowadays in cosmology and particle physics, Monte Carlo methods are very well used, simulation-based inference will similarly be a tool that we all use in a couple of decades' time, because it basically allows you to use machine learning methods in a way that scientists can interpret and say, I believe, and also allows you to harness the expressivity of them. So it both makes machine learning more like science and allows you to do science with machine learning from both directions. So that's what I would say is an interesting thing. There's a couple of interesting papers on the frontiers of simulation-based inference that I would recommend reading. There was a question up here. Yes?
Please tell us a bit more about, I missed the first 10 minutes, so I don't know what you said about what you're doing.
So a bit more about what I'm doing right now. So I work on a variety of things. So part of what I do is trying to measure this 21 centimeter line using a real telescope. So we're building, and we've got to the stage where we put the telescope in the Karoo and it blew away, and we installed the calibrator upside down and we turned it back right around. We've got first light and we're now processing that data, and we expect over the next 5 or 6 months to get a first measurement out of this. And in that sense, what we're trying to do is measure the first stars turning on using that 21 centimeter line. So using the CMB as a backlight across the whole sky to hear all the stars turning on for the first time in the radio spectrum. That sounds very easy, I'm sure, but it's actually the data analysis element is very, very challenging. And I build data analysis techniques and lead that team to do that. So that's my observational side. On the theoretical side, I like examining theories of the early universe, but that's more kind of a fun crossword problem for the weekends rather than it being sort of the job that I'm probably most well known for, which is the bit in the middle, namely designing better data analysis algorithms for doing this. In particular, what's called nested sampling, which is a technique for computing, amongst other things, numerical partition functions and performing model comparison. So model comparison is the idea that if you have two models of the universe, say one with dark energy and one without, or one with dark energy and one with a more sophisticated evolving model of dark energy, you ideally would fit those to the data and ask which one do the data prefer. Now, obviously, you can always get a better fit by adding more parameters. That, unless you've done it very badly, you will always get a better and better fit as you add more parameters. So what you want is a way of encoding the Occam's razor penalty that should come with the addition of extra parameters. And the Bayesian inference machinery, particularly when you do it correctly, when you have the state of the art in numerical techniques, automatically encodes Occam's razor and penalizes models with too many unnecessary parameters. Yes.
Thank you for your talk. Do you think that quantum field theory, vacuum energy, zero-point fluctuations offer a satisfactory explanation for dark energy?
So the question was, do quantum field theory, vacuum fluctuations, or vacuum energy offer a satisfying explanation for dark energy? The answer is a conclusive no. In fact, it's one of these things that people talk about being one of the most embarrassing predictions of theoretical physics. When you ask, what do our current understandings of quantum vacuum look like if you put it in as dark energy, you're about 10 to the 122 strong. So the value of the cosmological constant is embarrassingly small in a way that makes no sense with our current understanding of particle physics. It would be great if it were the Higgs boson, but it's not, because that's a scalar field that in principle could do this. Again, the Higgs boson is just way too strong. In fact, any understanding of normal particle physics predicts dark energy that is, 10 to the 100 too strong. So there are effectively two cosmological constant problems. There's A, why is it not zero? And B, given that it's not zero, why is it so small? And that is one of the big theoretical tensions in the early, theoretical tensions here that I've mentioned here, whose non-zero value is embarrassingly small. So it definitely doesn't. Maybe a complete picture of quantum field theory would explain dark energy, but currently at the moment, it just doesn't. Yes?
You mentioned in one of your slides that you think the universe is probably infinite to an extent. Do you think that if it's decided that the universe is in fact not flat, that might change? So are there two links?
Yes. So finitude and curvature is very much the same thing. So if you turn curvature on, the radius of the universe is about 42 megaparsecs, if you're interested. But flat models fit the data just as well. At least if you're a flat universe, so they do. So, but yes, if it's a flat, so of course you can't know the universe is infinite. And in fact, if I put my cards on the table, the universe is probably some bobbly potato-like structure, right? And it might be some undulating hills. And the question is our patch a flat bit or a curved bit upwards or a saddle shape or something similar? You'd only ever see our local patch, and therefore extrapolating to the entirety of the universe is a wild overestimation of the current statement about homogeneity and isotropy. But we do know that in our patch, it is very homogeneous, very isotropic, and very close to flat, and that needs to be explained. Yes. Yes, so the question is, by flat and curve, the meaning is Euclidean, non-Euclidean. So imagine the universe were two-dimensional. We could imagine us living on the plane, or living on a sphere, or living on a saddle, and then just add an extra dimension to that. So you just go up one. It could be us living on the four sphere or living on the four saddle, basically.
Okay, thanks for the questions. And thank you once again for the talk.